All right. Hello, everyone. Welcome to today's Machine Learning for Protein Engineers seminar. It's a great pleasure for us today to have Will here to talk about his recent works on enzyme design. Will received his bachelor degrees from McGill University and will complete his master's studies year in December. He's also a student researcher of MILA AI Institute. He has extensive research experience in graph neural networks before and has recently shifted his research focus to AI-driven protein design, especially for enzymes. So with this, let's welcome Will to talk about his recent projects on enzyme design. And Will, please take it from here.
Oh, yeah. Thanks, Liu and Megan for hosting this one. I'm really excited to introduce my recent works on enzyme design and with artificial intelligence. And first of all, I just want to thank David Baker, Dennis, and John for winning the 2024 Nobel Prize in chemistry. I think our work on AI-driven protein design would have been impossible without their foundational works, Rosetta and AlphaFold. Enzymes are really important. The enzymes are basically responsible for all metabolic pathways in living organisms. Basically, we have substrate molecules bind to enzymes, then they form some complex, and the enzyme will catalyze the substrate and transform the substrate into product molecule. Then the products just leave. But the thing is, catalytic process where the enzyme substrate binding is not equivalent to protein ligand binding, because there involves chemical transformations, and sometimes you do not need to have some perfect binding structure, perfect binding model for the reaction to happen. Sometimes you just induced fit structures would be sufficient. Oh yeah, and the challenge is is also mentioned by Paul Kim. He's a student of Baker's lab, working on protein design and enzyme design. Enzyme design is just extremely challenging, but also it is really important for therapeutic applications and solutions. There could be many ways for achieving de novo enzyme design, and I think my works were my approach is just one of the many solutions that might lead to the final de novo design. Yeah, so in this talk, I'm going to cover four works that I'm involved in, and on dataset construction, on modeling, also evaluation, enzyme retrieval, also the new philosophy that we should work more on reaction conditioned protein design or reaction conditioned enzyme design than the molecule binding protein design. This includes the ReactZyme. It is introduces a new data set, and the ReactZyme introduces a new data set and a retrieval based evaluation system, and we also did a lot of benchmarking on existing methods, including protein language models and molecular foundation models. Also, there's EnzymeFlow. we introduced a simulation-free, flow-based pocket design model for enzyme design. Also, we introduced like EnzymeFill, like a structured database. The datasets consist of more than 300,000 enzyme reaction pairs for this task. Then there's GENzyme. Basically, we develop a new generative model for enzyme design, starting from some given reaction. We generate the pockets, then we append the pockets to full protein to full enzymes. Then there's EnzymeCAGE. Basically, we developed a computational methods for enzyme function prediction and enzyme retrieval. There's a question. Oh, Leo had the question. Yeah, I'll skip the motivation part because we all know that enzyme design is really important, and in the age of artificial intelligence, we wanna be able to create our own enzymes with AI. Yeah, so basically the first one is a ReactZyme dataset. We collected enzyme reaction pairs, more than like close to 200,000 enzyme reaction pairs from Swiss prot and Re. And like we try to stay away from the EC, Go, or KEGG annotations. We just want to like focus purely on the enzyme reaction interactions. And so we like more than the data set itself, we proposed like a retrieval based ranking system, including top key accuracy, mean rank, and mean receptacle rank. Basically, our evaluation system ensures fairness in model comparison because it does not compare like discriminative powers of any models. Also, it debiases because we're not using any negative samples in evaluation. Just we're avoiding potential biases. Basically the retrieval evaluation system follows you like we have like candidates, we have a list of enzymes, and then we have a list of reactions. We just like assign like we just assign a confidence value. We just predict the confidence value between an enzyme and a reaction. Yeah, so we did a lot of benchmarks using protein language models and GNNs. Also, we compared with BLAST-P, and we also tried using contrastive learning here. We just did a lot of benchmarking, and we found deep learning can actually improve enzyme retrieval than the Euro like BLAST-P, like the traditional computational methods. Yeah, then there is generative models for active site design. Like we started like some people may ask why we like do not like generate like whole enzymes instead of the like active sites, because we think that like generating whole enzymes for like something is like could be extremely hard. Also, like starting, so we just like kind of divide this question into like sub problems. We started by designing the active site. Then we can like start then we can design the whole enzyme starting with the active site. That's why we propose like some generative models for active site design. Yeah, but like for doing it, we gotta have our own data sets, right? So we proposed that like we introduced a new data set called the EnzymeFlow, consists of more than 300,000 enzyme reaction pairs with the pocket structures collected from Rigi, Metasac, and Brenda. We find this, we annotate this catalytic pockets with ligand transplantation algorithm using EnzymeFill. Yeah, then the core thing in our model is we introduced the enzyme reaction co-evolution. First, I just want to talk about perhaps you all know what a protein evolution is, so I'll just skip this part. Then there's enzyme reaction co-evolution that we used in our model. So enzyme reaction co-evolution, this idea is basically used to capture the reaction specificity in the catalytic reaction. So you can imagine if enzymes A and B can catalyze one reaction A, there may be evolutionary information linking this to enzymes. Or similarly, if enzyme A can catalyze reactions 1 and 2, there may be evolutionary connections between these reactions, you can imagine. So this concept extends to a broader idea of enzyme reaction co-evolutionary information. It is similar to the protein evolution, where we use multi-sequence alignments to align the enzymes and reaction pairs, and we just encode them using our using our co-evolutionary dictionary. Then there is another part is a flow matching. So flow matching is a simulation-free approach to learning and deterministic continuous time dynamics, and just matching invariant target distributions on SU3. This is first proposed in fold flow, where they use flow matching to design proteins. And basically what they do just interpolate between a random state and a structured protein state. Then there's an enzyme flow. The enzyme flow is proposed to generate the catalytic pockets, amino acid types, the enzyme commission number, also the enzyme reaction co-evolution. What we did is we pre-trained the enzyme flow first on the protein backbones, figure 1 here. Then we continuously pre-train it on protein ligand complexes in the PDB bind dataset with a complex structure. Then we fine tune it on our EnzymeFill pockets to allow the model to generate the catalytic pockets conditioned on the reaction. And the enzyme reaction co-evolution, also the EC class, the EC number are encoded in the model learning process. Yeah, so it's just some visualization of how enzyme flow works, just starting from a completely noise. Everything is conditioned on the reaction. So basically starting from a complete noise, we co-design the structure as well as the pocket sequence. And for the pocket sequence part, we employ the Markov transitions proposed in multiflow. Yeah, here are some visualizations. Basically, the enzyme flow, just we compared it between RF diffusion all atom and in the pocket flow. We show that EnzymeFlow can generate the pockets with lower RMSDs and higher like alignment score, like TM alignment scores. I'll skip the table. Yeah, also we show some function results, and we were able to like generate the like pockets that can better match the enzyme commission number than the baseline methods. And then we move on to the enzyme design with the generative AI. Like EnzymeFlow is something that designs your pockets, and this one we want to leverage we leverage EnzymeFlow. We design the pocket first, then we append the pockets to full enzymes. Because like we wanna use models to improve our understanding of how enzymes interact with substrates during catalysis, and maybe can contribute to understanding metabolic pathways and really potentially aiding like help improving therapeutic interventions. Yeah, here's how GENzyme works. GENzyme is a de novo enzyme design model, like conditioned on any unseen reaction. So basically, you gave some catalytic reaction, and the GENzymeFlow designs the pocket for you as well as the pocket sequence. Then GENzyme appends the pockets into full enzyme structures, as well as then it does like a inverse folding to just like to predict to generate the enzyme sequence. Also, we have some binding module that predicts the final the pocket of where like the pocket based enzyme substrate complex. Yeah, here's how we train GENzyme. GENzyme basically has two components. One is the pocket design module, and the second one is the pocket implanting module. Basically, we first pre-train them separately, then we just make them together and fine tune the whole module with like some small perturbation, like small noises. So basically, like by doing the condition on some reactions, GENzyme can give you the full enzyme as well as the enzyme substrate complex. Here are some. I didn't put the tabular results. You can find the tabular result, like the table results, in our paper. But here we generate we realize some like results generated by GENzyme. Lab one is how GENzyme works. Basically, here is first we design some pockets conditioned on the reaction, and then we can append the pockets, and we rank the like append pockets to full enzymes. Then we can rank the full like the enzymes by their PTM score or PLDVT score. And figure A just shows some like some complex structures between the pockets and the substrate, also the pockets and the products. And in the right one show you some generative structures by GENzyme. The left ones are ground truth structures with pocket structures, and the right one is something we generated using GENzyme and rank them by TPM PTM score, and we observed that like the structures, the generated structures with high PTM scores can look really really similar to the ground truth enzyme. So we find it overall it's pretty exciting. And then there comes like the function annotation and enzyme reaction prediction or enzyme retrieval. Basically, we have some like generated pockets and generated enzymes. Like how do we evaluate them before we conduct wet lab experiments, right? So basically, we also proposed a new method for function annotation, enzyme reaction prediction, and enzyme retrieval. Maybe there's a question. Oh, okay. Yeah. Yeah, like we call it EnzymeCAGE, but anyways, this one is used for enzyme selection and filtering. Also, like the model is trained by using positive enzyme reaction pairs and also negative enzyme reaction pairs through some like pocket specificity mechanisms and the contrastive learning approach. This is something I proposed in the EnzymeFlow paper that we should like instead of like current complete method learns like uses full enzyme structures, but I think we should just focus on the catalytic pockets where the active sites to determine to do the filtering to select enzymes for us. So it's something that the pocket specific augmented retrieval model is something I have in EnzymeFlow in the appendix section. Yeah, and to do like EnzymeCAGE is basically something like that does the job does the pocket specific enzyme retrieval and enzyme function prediction. So we call it EnzymeCAGE. Basically, it refers to catalytic specified geometrically enhanced enzyme reaction prediction model. EnzymeCAGE can be used for function prediction for unseen enzymes, or enzyme retrieval, or enzyme recruitment for orphan reactions. Basically, what it does is, sorry here, you gave some basically what it does is you gave some enzyme and you gave some like chemical reaction. The EnzymeCAGE identifies the active sites, the catalytic pockets. Then it processes the catalytic pockets with some geometric encoders. Also, it processes the chemical reaction with some geometric encoders. Then we do like a fusion here, like a cross attention here between the enzyme pockets and the chemical reaction. Then it just generates like some confidence here, confidence value, or we call it catalytic score here. So it can be used for for function prediction for novel enzymes, or enzyme recruitment or enzyme retrieval for new reactions. We're going to evaluate EnzymeCAGE. We're going to evaluate EnzymeFlow and GENzyme with EnzymeCAGE function annotation model. Yeah, so basically we show some function prediction performance using binary classification. Also the sorry, B is I used the wrong one. Also like the enrichment evaluation, also the top case success rate. We show that EnzymeCAGE can just in terms of function prediction, it shows like really improve the state of the art's performance than current methods, including EnzymeZyme, BlastP, ESP, Clean, and GVP fingerprints. Like figure F here, just showing like by learning the pocket structures, EnzymeCAGE can accurately predict functionally similar enzymes. So it was just with like huge structure difference. You see here, like the I mean here, yeah, there's a chat. Oh, I'll look at it later. Yeah, also here are like some function prediction results, and here are some like the enzyme retrieval or recruitment performance. We we rank them like we evaluate by using top case success rate, including top 1, top 3, top 5, and top 10. We can just observe that like EnzymeCAGE does like really excellent job here, like uh like better results and better recruitment success rates. Also, we do some case studies show that EnzymeCAGE can really can recruit can retrieve positive enzymes among like a long list of candidates. Yeah, also some work in progress. It's something like enzyme generator is something I work in progress. There are some like judgments from iClear saying that like we should do some like wet lab experiments. I agree. I really agree with a reviewer. I mean, the enzyme generator, the thing that I'm currently doing is train on evolutionary scales and the enzyme fitness landscape. The enzyme generator uses EnzymeFlow and GENzyme as scoring and filtering functions. Also, it uses EnzymeCAGE for computational screening, like the for enzyme retrieval, also and selection. And after like filtering by EnzymeFlow and EnzymeCAGE, we can send the generated enzymes by enzyme generator to wet lab for really wet lab validations. Oh yeah, then there's right, there's 30 minutes. I'll wrap up and it's time for questions.
All right. Thank you so much for the talk, Will. I think now we can move to the Q&A session. And for all the audience, you can unmute and ask, or you can just write your questions in the chat. If there is no question in the chat now, maybe I can start with a general question. Is that possible you can go to your EnzymeFlow part and give us more details about how do you design your model and how you model each modality, like structure, sequence, and like the overall training stuff?
Oh, here.
Yeah. Can you just give us more details about what you're doing here?
Oh, okay. I mean, there aren't like too much. I don't know what your backgrounds are, but like basically, could you elaborate on the sequence alignments of reaction styles in the code? Oh yeah, sure. Oh, just yeah, here the sequence alignment, we just represent the reactions by reaction small by small strings, and we just do alignments like similar to MSAs. Does it like answer your question? The co-evolutionary workflow? Or except for the EnzymeCAGE, is there any part of the prediction that has a validation? Not really. Not really, because it's really expensive for us to do wet lab validations. But we will expect wet lab experiments validations in the enzyme generator, because it's like a workflow. First, we have some generative models, then we have some scoring functions. Then we can combine the generative models and the scoring function. Then it can give us some like confident predictions. We can then send it to the to wet lab for validations, right? Really excited to try EnzymeCAGE. Was wondering if you had any idea when you plan to release. Oh yeah, we plan to release it in 2 weeks. We're like in early December. We're just preparing the manuscript right now. Maybe I didn't follow correctly. I'm curious what mission you use plugin painting. Oh, okay. Okay, yeah, basically the pocket painting could be you can use uh RF diffusion algorithm for pocket painting, but our like or Genie 2, or like there are currently like protein foundation models can do the pocket painting thing, right? We chose to use ESM3 to do the pocket painting, and but like you cannot directly use it. You have to fine tune it on certain data sets, because like it's some pre-trained foundation models. Then just to fine tune it for downstream tasks. So basically, what we did is we fine tuned the ESM3 on EnzymeFill for the pocket painting task. Basically, what it does is it has some like VQVE model that translates the structure, the coordinates into some tokens, and the model just imping the top tokens. Then it just after like impending, it does decode, like it decodes the tokens into full structures. Also, with multi-flow, you get pocket structures jointly. Then for painting, you do sequential design. Why have you gone with sequence?
Yeah,
Well,
sorry. I can also unmute if you didn't understand. For some reason, I assume. Oh, can you hear me? Yeah.
Yeah.
For some reason, I assume that for the pocket in painting, you did sequential. But then if you're using ESM3, then I assume you're doing actually jointly too. Then.
Yeah, so what we do, like,
Okay.
yeah, jointly we do, like, because you have to find, like, we tried the ESM3 without fine tuning it. It just basically it destroys the pocket. It just completely destroys it. So we had to fine tune it on EnzymeFill for this task.
All right. Okay. Thank
you. Yeah. Yeah. Also, the impending one. The impending one is like not only condition on the pocket structure, but also condition on the pocket sequence. Yeah, like there are better method than EnzymeFlow to identify the catalytic pockets. So basically, we use a synthetic or like synthetic annotations for pockets. This is hard because we don't have too much like experimentally validated data for the task. We just go where data can lead us to, right?
All right. If there's no more questions, I think I'd like to thank Will again for giving this amazing talk today. And thank you everyone for joining us. And I really hope you enjoyed the session. And next week, we'll have Jing Su from Westlake University talking about his recent project model. So, and we will see you next Tuesday. Thank you, everyone.
Thanks, everyone.